Hey everyone, welcome to this video where we're going to talk about how to solve this surface integral problem. So the question says, let F be the following vector field, and we want to find the closed surface S on R3, which maximizes the value of the outward flux integral. So that was a lot of words. Let's really figure out what we're trying to do. So we're given this surface integral and we're trying to find S. How do we do that? It's not super straightforward, but the best advice I can give for these kinds of problems where you're not super sure how to start is to look at all the formulas that you've learned so far in this chapter about vector calculus and see which ones you can apply to the surface integral. One that jumps out at me is the divergence theorem, which states that surface integral over f is equivalent to the triple integral of the divergence of f over a solid E. So we don't really know what E is yet, but knowing E can help us find S. So let's try and see what we can find. We can calculate the divergence of F. It's going to be the partial of x of this first term plus the partial of y of the second term and the partial of z of the third term. And we know all this because divergence of f is the gradient operator dotted with f. And so if we compute all this out, we get 1 minus 2x squared plus negative 4y squared plus negative 8z squared. And I'm going to write that a little bit neater by taking out all the pluses when it should be negative, like that. So now we have our divergence of f. And to get the maximum value of an integral, we want to integrate over something that matches this divergence of f curve as closely as possible, like covers all of it. Divergence of f is a function, so we can draw our xyz planes, and we see that divergence of f has the form of an ellipsoid. So it's going to look something like this, oops, where there are ellipses all over. So it's kind of like a sphere, but like you stretched it out on one end. So that's our divergence of f. And to get the maximum integral value over this divergence, we want to integrate over this surface. So since we want whatever we're integrating over to try and match div f as closely as possible to get all of the div f that we can, we want E, our solid, to be this shape and all the volume inside it. So that's gonna equal 1 minus 2x squared minus 4y squared minus 8z squared greater than equal to 0. Why do we put greater than or equal to 0? Because we're trying to get all of the volume inside this surface. If we had some parts of this that were less than 0, then it would be like negative volume almost, like we don't want to go there. According to the divergence theorem that we defined up here, we know that the surface S is essentially the surface over our solid E. So S would have the equation 1 minus 2x squared minus 4y squared minus 8z squared equals 0. Not greater than or equal to, equals. Because we're just trying to get the surface, but not the interior of our ellipsoid. And that's it. We know that it's closed because we can see from that ellipsoid that it is closed. So hopefully this made sense. If you have any questions, please leave them down in the comments and let me know if there are any other problems that you'd like me to solve. Thanks for watching.